Hello, good evening. It seems no one is there. So let me just wait for another 4 or 5 minutes so that at least a few students will be joining. I hope. Let me just wait for another 5 minutes. Okay, no one is there, but still, let me go about. Today's topic is about the second part of LAO, linear algebra and optimization, namely optimization techniques. So we are going to start with the introduction, formulation of an LPP, linear programming problem, because here we formulate the problem in terms of linear equations or linear equation of an objective function to be optimized, subject to the constraints, which will be either linear equations or mostly inequalities. So it's going to be therefore called a linear programming problem, or shortly LPP. So how we formulate the problem and then how we solve. Of course, there are various methods to solve such LPP. And initially we will be solving using graphical method. Then we will have a distinction between graphical procedure or graphical method to algebraic method. And under algebraic methods, what are various methods are available according to your syllabus? We will be starting with one of such methods, a famous one, namely simplex method, and so on. So let me go about sharing in detail what is LPP. How do we formulate the problem? So how do we solve? Basically by graphical method and so on. So as I said, the graphical procedure is going to be the first one to have your LPP solved. So we have determination of FSS, that is feasible solution space. Determination of the optimum solution from among all the feasible points in the solution space. So what we do, we take the objective function to be optimized, maximized or minimized. And then we take the constraints which are inequalities, but then we take the equations to represent them as straight lines in the first quadrant of a graphical representation. So you have the critical, you have the intersection of those straight lines a common space that is called a feasible solution space. And from that, you have the corner points. And from those points, you will be able to obtain by solving the two equations by taking two at a time. So when you are solving them, you are getting the point as you plot the point on the graph in the first quadrant or any two-dimensional plane. So then from those points, you are finding the objective function value at those points, of which you take the maximum. The function is to be maximized, or minimum if it is to be minimized. So generally it is to be optimized. So such a common space, feasible region is called a feasible solution space. So from that space and the points that are available in the feasible solution space, you take the optimum solution, and that is applicable to your question. So what is infeasibility? So there is no feasible solution area. That is, there are no points that satisfy all constraints of the problem. An infeasible LP problem, linear programming problem, with the two decision variables can be identified through its graph. Therefore, when you are not able to get the points or the decision variables are nothing but the unknowns, the variables, say x1, x2, x3, or x1, x2, depending upon the nature of the question. And if they don't have any common region to share, that is a feasible solution space, then there are no points that satisfy all the constraints of the problem. That means there is no feasible solution. So that's such a case will therefore be called an infeasible solution. Therefore, it is generally called an infeasibility. Before we go to all those things, unboundedness, etc., let us first take the characteristics of an LPP. What are the terms that you are associated with? Feasible region, the set of points that satisfies all constraints, interior points, boundary points, corner or extreme points. Such of those points will form the feasible region. These points are obtained by solving any two equations at the intersection. Optimal, and those side lines are nothing but the constraints with respect to which are subject to which you need to optimize the given objective function. Optimal solution. The corner point with the best objective function value is optimal. So in some, you may come across with 3 or 4 corner points which are in the feasible solution space or feasible region. So you will have that particular point which is best suitable to the objective function is your optimal value or optimal solution. So there are two types of possibilities: unique optimal solution, alternative or multiple optimal solutions. So after seeing unique optimal solution, we will come back to this multiple optimal solutions. Okay. Algebraic method. So in graphical method, as I just mentioned, you have graphical representation on a plane, most preferably, or preferably you have only the first quadrant, because you have the decision variables x1, x2, or x1, x2, x1, x2 only, because you have the plane 2 dimension greater than or equal to 0. Non-negative decision variables. Therefore, which is possible only in your first quadrant. So we plot the points, we plot the straight lines of the constraints, which are normally inequalities, but then we take them as equation. Therefore, the area just prior to the boundary will be less than or equal to. So that is your constraint. So from among the equations, I will show you the graphical solution later. You have the region which is common to all such straight lines, and then you are finding the corner points and which gives the best solution, which is the maximum value, that is the maximum value of the objective function to be optimized. Minimum value gives the minimum minimization. So having gone through the graphical method, I will give some examples later. Now let's go to algebraic method. So here we have LPP, the linear programming problem, in to be written in standard form. What is meant by standard form? We see we will be making use of some conditions, that how the constraints must be, how the objective function must be, and we will be introducing some variables such as slack, surplus, when do we do it, what do you do with the slack, and what will you do with the surplus. All these things will appear. FS, feasible solution. PS basic solution. BFS, basic feasible solution. OBFS, optimal basic feasible solution. And one such methods, as I said, we are going to see according to your syllabus, some two-phase method, a dual simplex method, some special cases are there. And then the best thing are widely used algebraic method in solving an LPP is simplex method. Okay. Now, the optimal solution, if it exists, is a corner point, which we already discussed. Have NCM ways of finding the corner point if there are M equations in N unknowns. Simplex takes just a fraction of the above. Okay, it takes iterative. It is iterative and simple. General form of an LPP. So when we talk about much about LPP, what is a general form? How does a problem, linear programming problem, will look like? Or what is meant by formulation of an LPP? Okay, the general LPP, linear programming problem, LPP, is to find a vector. Here vector means a row or a column matrix, which we say normally a vector having components, say n, x1, x2, x, etc., xn. That means there are n unknowns, okay, which optimizes maximum or minimum. The objective function is equal to c1 x1 plus c2 x2 plus c3 x3 plus etc. plus cn xn. So you have a linear combination of the components of the vector which are to be found, which maximizes or minimizes, in other words, in general, optimizes the objective function Z. So capital Z is a reserved symbol for writing objective function to denote something like you write normally small f function. Here we use capital Z. Okay, right. In terms of the unknowns x1, x2, etc., xn, where c1, c2, c3 are constants subject to linear constraints. So constraints are nothing but the conditions. Constraints are nothing but conditions. So what are they? A11 x1 plus A12 x2 plus etc. plus A1 and xn less than or equal to or greater than or equal to or equal to B1. You know very well, you always have the solution is obtained from the matrix equation AX equal to B. Capital A stands for matrix of coefficients, which are usually written as in a simple form Aij, small a suffix Aij. I stands for rows, J stands for columns. With which if you expand, you will write capital A equal to A11, A12, etc., A1n, A21, A22, etc., A2n, etc., etc., AM1, AM2, etc., AMN. If it is a m by n, that means if there are m equations, linear equations in n unknowns. Is it right? And you know very well, x is nothing but the column vector x1, x2, etc., xn equal to the column vector of constants b1, b2, etc., bm. Isn't it? Or if it is, it should be bm. So a21 x1 plus a22 x2 etc. plus a2 and xn less than or equal to or greater than or equal to b2, etc. am1 x1 plus am2 x2 plus etc. plus amn x equal to less than or equal to or greater than or equal to bm. Okay, and xi greater than or equal to 0. See, these unknowns are in LPP parlance are known as decision variables because they are not just variables which normally we pronounce as, and they decide, they give the decision about the objective function whether it has the maximum value at this point or the maximum value of the function or minimum value of the function. It decides. That's why they are also called decision variables. Remember, they are all non-negative. They are all non-negative, greater than or equal to 0. This is the general formulation of an LPP solution. So what is the solution? X. Ax equal to b gives you the solution x, a column vector having 2 components or 3 components or in general n components depending upon the nature of the number of linear equations in your system. So any set x1, x2, x3, xn of real numbers which satisfies the constraints in the general LPP which we have just discussed is called solution of general LPP. Feasible solution. So of the solution, that is the components of the vector, which one is called a feasible solution? Any solution to a general LPP which also satisfies the non-negativity restrictions of the problem is called a feasible solution. So what is the non-negativity? X1, X2, etc., Xn, each one is greater than or equal to 0. It's non-negative. So it should also satisfy the non-negativity of the decision variable restriction. Then it becomes feasible solution. Basic solution. This solution is obtained by this solution is obtained by setting any n variables among m plus n variables equal to 0 and solving for remaining m variables, provided the determinant of the coefficients of these variables is non-zero. Such m variables are called basic variables and remaining n zero-valued variables are called non-basic variables. So in short, the non-zero variables are called remaining n zero-valued variables are called non-basic variables. So basic variables means which are very essential. They should be non-zero. So the other variables which are zero to start with will be called non-basic variables. So you just look at the determinant of the coefficients of these variables is non-zero. Such m variables are called basic variables and remaining n zero-valued variables are called non-basic variables. Okay, basic variables are those whose determinant of the coefficients such that the determinant of the coefficients of such variables is non-zero. And the remaining variables which are zero-valued are called non-basic. In the sense, basic which are non-zero are important. So they are called basic variable, important variable. They form the basis. And others are non-basic. Okay. Now we are going to see in practical problems what do we normally take, what are the basic variables, non-basic variables. So in practice, how we go about, we'll see. Now basic feasible solution, BFS. It's a basic solution which also satisfies the non-negativity restriction. That is, all the basic variables are greater than or equal to 0. That is very important. You find basic solution and then it should also, the solution you have satisfies all the constraints, becomes feasible. Then when it also satisfies the condition that the decision variables are satisfying the conditions of the non-negativity restriction. That is, basic variables are greater than or equal to 0. x1, x2 greater than or equal to 0. Then it becomes BFS, basic feasible solution. BFS, that is the basic feasible solution, are of two types. If one or more basic variables are 0, we call it as degenerate BFS. If all basic variables are non-zero, then we can non-degenerate BFS. Optimal BFS. We are always interested in finding optimal solution. BFS which optimizes the objective function. See, of the solutions that you find, as I mentioned, suppose you do it by graphically. Now, suppose you have in the feasible solution space, that is feasible region, about 3 or 4 corner points at which you are finding the values of the objective function. Only one point will be there at which the function will be maximum. Maybe at another point it is maximum. So that point that decides that the optimization, either maximization or minimization, is the optimal BFS. Slack variable. Variable added to a less than or equal to constraint to convert it to an equation is called a slack variable. So slack means something is lagging, isn't it? There is some slackness. There is some dullness. There is something needed, isn't it? So in order to make it invariably, you will be having the constraints in general of the form less than or equal to, at times greater than or equal to. Anyway, you should make it to be an equation. So when you will be making it as an equation, when there is something less than or equal to, only that is something less than or equal to means only when you add something more, it goes to the equality. It's already lagging. It is already, there is a slackness. So you add something so that it goes to equality. Same way, next you are going to see surplus variable. There is already greater than or equal to. It is more than what is required. It is more than what you have, what you need to have. So there is surplus. So that is to be subtracted so that is balanced. So if you are having more than, that is greater than or equal to. So you subtract. What is being subtracted? Something surplus. So you make it equal. Here is already there is lagging. Something you need to give more input. So if you add, it becomes balanced. So that way you have to remember. So when you add a variable to less than or equal to constraint, it is getting converted in equation. Such a variable is called a slack variable. And when you have greater than or equal to inequality, in order to make it an equality, you remove something. What is removed? Surplus. What is excess is to be removed. And that is called a surplus variable. A slack variable represents unused resources. A slack variable contributes nothing to the objective function value. Because in your objective function, you have only decision variables in the beginning. In order to make the constraints in a standard form, we do these types of adjustments. So it will not come into the picture of finally whether slack variable or surplus variable to get any value to be added to your objective function. They have no play to give any value to your objective function. They are just coming into the picture, and you will have some procedure to replace non-basic, basic variables, like all those things that we are going to see in detail. Anyway, so that will not be making any change in your objective function value. These are all only a kind of auxiliary variables that are coming in and going out, and to help you to get the optimization or the maximum minimum values of your Z, which is only made up of decision variables. Okay, right. Surplus variable, as I just mentioned, variable subtracted from a greater than or equal to constant. So when there is something more, something excess, something more, you need to subtract. You take it out. There is surplus. You have to make it balanced. You bring it to equality. So you remove something. See, you are measuring. You are asking for a half kg of an item, and the merchant puts something on the scale. it shows 600 grams. So what is extra now? 100 gram. It is to be removed. It is surplus because you need to be going only 500. Is it right? So that is removed. It is greater than 500. So that is removed. Suppose you have only 400. Suppose he puts at one stroke in the scale and then he measures. It shows only 400 grams. But you ask for 500 grams. So he has to now add slack. You add so that it becomes 500. When it is less than, you add to make it equal. When it is more than, you remove to make it equal. That's something. So variable subtracted from a greater than or equal to constraint to convert it into an equation is called a surplus variable. As above, as before, a surplus variable represents an excess above a constraint requirement level. It is more than what is required, the excess. It contributes nothing to the calculated value of the objective function like your slack variable. Okay. They are almost dummies. They are not rummies. Right. So this is what again we come back to summarizing what an LPP or how LOL and LPP looks like. What is its formulation? A standard maximization problem is one in which the objective function is to be maximized. If it is a minimization form, then converted into a maximization. All the constraints are expressed in the form of equations, except for the non-negative restrictions. Non-negative restrictions means for the decision variables, which we will not be making any compromise, any equality. We will just put them as greater than or equal to 0 because we want them to have the constraints to have such a non-negativity restriction. That's why it is used the term here, except for the non-negative restrictions by introducing slack and surplus variable. So except for the non-negative restriction. So forget it. All other constraints expressed in the form of equations. How? Normally it is given either less than or equal to or greater than or equal to, but by introducing slack and surplus variable, depending upon the nature, it makes to be, they are all made to be an equation. The RHS of each constraint equation is non-negative. That is also to be taken into account. So the right-hand side constant should also be non-negative. All the variables are non-negative. Variables mean decision variables, x1, x2, etc. So such a linear programming problem, the conditions that we have listed out here satisfies. It's called a standard linear programming problem. Okay. So this itself is a simple question that can be asked for just 2-3 marks, or maybe in quiz also. How to rewrite the following LPP in the standard form. That's important. In the standard form. Question is maximize z equal to objective function 2x1 plus 3x2 plus 4x3 subject to the constraints x1 plus 3x2 plus 5x3 less than or equal to 10. 3x1 minus x2 minus 2x3 less than or equal to minus 4. x1 less than or equal to 0. x2 comma x3 greater than or equal to 0. Okay, right. Now, solution. First, we start keeping in mind that all the constants on the right hand side of the inequalities must be non-negative. It should be only positive. It can be 0. It should not be negative. So non-negative. Okay, it can be 0. Right. Multiply the second constraint by -1 because on the right hand side you go -4. So when you multiply by -1, what's happening? Minus 3x1 plus x2 plus 2x3 is greater than or equal to +4. It is actually greater than or equal to, okay? Greater than or equal to 4. I put it greater than or equal to. Okay. Now, given, okay, that is over now. So minus 3x1. First, let us see. It is not entirely over as of now. Having seen the right hand side constant being negative, multiplied by minus 1 throughout, we are getting this minus 3x1 plus x2 plus 2x3 greater than or equal to 4. So one condition is okay. But again, go for the decision variables condition. X1 less than or equal to 0, x2, x3 greater than or equal to 0. Well, x2, x3, each one of them is greater than or equal to 0. That is, decision variables are non-negative, fine. But x1 less than or equal to 0 should not be. Okay. So decision variables should be non-negative. That is very important. Okay. So you have to go for some substitution. Just close the video because no one is there. Okay. Wait. Now just look at, okay, given x1 less than or equal to 0. So one of the three decision variables, x1 is less than or equal to 0 should not be the case because decision variable should all be non-negative. So what you must do, you may ask one question. Same thing can be done. Multiply throughout by minus. Because inequality less than or equal to will become greater than or equal to x1 will become minus x1. So that minus x1 you can put it as a new variable instead of because you should not have the variable with a minus sign. So you can name it by another variable. Okay. So minus you just write minus x1 greater than or equal to 0. That minus x1 you change it as x1 dash. Okay. Minus x1 as x1 dash. Thus the problem becomes now. You just look at now. Maximize is that equal to. Now you are having x1 2x1, but when you put minus x1 as x1 dash, what is x1? Minus x1 dash. Isn't that? Okay. So minus 2x1 dash. In the objective problem, you can have nothing wrong because x1 dash is after all minus x1. Is it right? So when you are finding x1 dash, it will be minus your x1. So you can find the unknowns or decision variables. So you can now put minus 2x1 dash. Only in the constraints, you should not have them. You can have negative sign, but the constraint should not be greater than or equal to, and each of the variables should be, original variable must be greater than or equal to 0. See, don't get perplexed. If you just look at minus 2x1 dash, you write it as it now. I will tell you. Plus 3x2 as it is, because x2 is greater than or equal to 0, plus 4x3. Okay. Now you are asking minus 2x1 dash. Can you have minus 2? Minus x1 dash? Yes. Because minus x1 dash is nothing but x1. Isn't that? So your minus x1 dash is nothing but x1. So you are preserving positivity for your original decision variable. Don't bother about x1 dash. Okay. Now, subject to the constraints, now look at. In the place of x1, you have minus x1 dash because minus x1 is x1 dash. So x1 will be therefore be minus x1 dash plus 3x2. Then again you may ask one question, sir, this is confusing. Plus 3x2 plus 5x3, okay, less than or equal to, okay, right hand side is positive. But you only said, sir, the decision variable should not be negative. Minus x1 dash is showing that x1 dash is negative. But x1 dash is something that we have substituted. Minus x1 dash is nothing but your x1. So when x1 dash minus x1 dash is nothing but x1. So but x1 is less than or equal to 0. So minus x1 dash will be greater than or equal to 0. So that portion is now becoming greater than or equal to 0. Okay, right. Next one. 3x1 dash, because you have minus 3x1. Where minus x1 is nothing but x1 dash. So minus plus 3x1 dash plus x2 plus 2x3 greater than or equal to 4. Already we have made. And look at the last non-negativity constraints of the decision variables. X1 is less than or equal to 0, but minus x1, that is x1 dash, is greater than or equal to 0. X2 dash is greater, x2 is greater than or equal to 0, x3 equals 0. Therefore, the last decision variables non-negativity is reflected now as x1 dash, comma x2, comma x3 greater than or equal to 0. Hope you might have understood now. Again, finally, we change the constraints to equalities. Once those two conditions are taken care of, we now go for changing the constraints to equalities. Is it right? See, this is how we go for writing or rewriting given LPP into its standard form. Right. So, by introducing a slack variable and a surplus variable. And remember here, it is not necessary that you should have only one slack variable and only one surplus variable. It all depends on how you are having your constraints. If you just go back, just see that there are two constraints. Don't bother about the last one. Last one is always about the decision variables non-negativity. Okay, that is also important. So that is taken care of. So when it comes to the number of constraints, it is only two. So here again, don't be under the impression that so there are three unknowns, but there are only two constraints. That's not a problem. Okay, that's the reason why we don't do it by basic or customary algebraic method of solving three equations in three unknowns and solving the linear equations by, already you know very well, you are familiar with solving by Gauss elimination method, elimination first and then back substitution. And you know, fundamentally some substitution method, all those things you know very well. But here we go about in a different manner by solving the LPP by different algebraic methods. Before that, we need to write them in the standard form. So here, so don't bother about the number of constraints and the number of unknowns. Okay, right. So here now, okay. So what do we do? What I was trying to say, just look at, you have less than or equal to, you have greater than or equal to. So don't bother about this one. This is all about ensuring that the decision variables are non-negative. X1 is less than or equal to 0. That is 0 or negative. Negativity is there. So we make it minus x1 to be x1 dash, so that this is x1 dash, which is the new variable, which is greater than or equal to 0. Already x2, x3 are greater than 0. So we have ensured that the decision variables are non-negative. We have also ensured that the right-hand side of the constraints, there are only two constraints, are positive. Okay, by introducing first by multiplying by -1 here and then by multiplying by minus again here, because there one of the decision variables is negative. So having done this much, here there is only one less than or equal to, there is only one greater than or equal to. Therefore, whenever A constraint is having less than or equal to inequality means something is to be filled in. Something is to be added so as to make it equal. It is already less. There is a shortage. So fill it. So put it. Fix it. You add it in order to make it equal. Just now I gave you an example to make it equality. You had a 400. You asked for 500. So you need to add 100. So that is being added by a variable called slack variable. Slack, first letter S, therefore it is denoted by S. Being the first variable, it is S1. Then you go to the second constraint, in which you have the inequality greater than or equal to. So that something is excess now, something more. 600 grams, you asked for 500 only. So you remove 400. That is surplus. 100 grams is surplus. You will be paying only for 500 grams which you asked for. So you need to remove in order to make it equal. Is it right? So here is one variable needed to be added. Here is one variable to be subtracted from. And this is slack, and here it is surplus. Both are, of course, having first letter S. So one we can take S1, another we can take S2. So what's happening now? Maximize is equal to, you write the same, minus 2x1 dash plus 3x2 plus 4x3 subject to the constraints minus x1 dash plus 3x2 plus 5x3. We had less than or equal to 10. So you add which variable? Slack variable S1 equal to, now it is now compensate that. We added balanced equal to 10. Go to the next. We had a 3x1 dash plus x2 plus 2x3 greater than or equal to 4. Already it was excess. So remove the surplus minus add slack. Whatever is shortage, you add in order to make it balanced. Whatever is excess, remove it. Surplus, remove it in order to make it balanced. So minus, since it is the second variable in the list 2 equal to 4. So x1 you write as usual, the third x1 dash x2 x3 x1. Now you have to include s1 s2 also in your third constraint list. Okay, so that is understood that the slack variable and surplus variable should be non-negative. So automatically you can write x1 dash x2 x3 which you had already, comma s1 comma s2 greater than or equal to 0. This is how we write the given LPP first in the standard. So similarly, you have another example, change the following LPP into standard. Okay. Now, we'll see it in detail, because here there is a slight change or extra fitting in your decision variables at the end, the last line. So what does it mean? That also you should know. Just because other things, of course, you are being very familiar with now. Minimize is equal to 2x1 plus 2x2 plus 4x3 plus x4. Here are 4 decision variables subject to the constraints. See, remember here, there are 4 unknowns. There are 4 decision variables to be solved, to be found out. But there are only 2 conditions. So you don't need to worry about the number of constraints and the number of decision variables. Okay, right. So 3x1 plus 2x2 plus x3 plus 9x4 less than 16. Well, right hand side is positive. Left hand and then first thing that is okay. Next 7x1 plus 2x2 plus 4x3 plus x4 less than or equal to 24. Fine. Okay. So the constraints can be less than or equal to or greater than or equal to. So that you don't need to bother. First thing you ensure that the right hand side constants are non-negative. Fine. Now go to the decision variables. X1, X2, X3 greater than or equal to 0. X4 unrestricted. What's the meaning? That we'll see. Okay. And also you must see that there is a term, there is a word minimize. Now how we change when you are doing it in the standard form. Okay. In the maximization, there is no problem. You will write maximize. Okay. Just look at. When it comes to rewriting The minimization problem should also be converted into maximization automatically. When will you do? So you have to create a new variable so that that is equal to minus of your minimize. So minimize Z is nothing but maximize W. That's also a standard reserved symbol where W is minus Z. So when you take negative of this minimize, that is reflecting your maximization. Okay, right. So let's go now. The objective function has to be written as, look at, maximize W. So W is something that you have introduced. The problem should be written in standard form, only maximization. So maximize. So you cannot put Z because the problem is only minimize Z. So you cannot write minimize Z as maximize Z. Okay. You need to, of course, find minimum value, but that is originally to be written as maximize with a new variable W. That's also a standard variable which we cannot write as we feel. Okay, W. But W cannot be Z, isn't it? So when you take minus Z, that is your new variable because it has to be transformed from minimization to maximization. So when you want to maximize in order to standardize by introducing the new variable W in terms of the Z that is available in your question. So minimizing Z is the same as maximizing W, where W is minus Z. So what is minus Z? When Z is 2x1 plus 2x2 plus 4x3 plus x4, minus Z will be multiplying throughout by minus. Now, okay, right. That is simple. Now, all other things, of course, you have right hand side constants are non-negative, and your decision variables are also positive, x1, x2, x3. But x4, there is one term given, unrestricted. There is no restriction. Okay. So, how it is to be written? Right, x4 is equal to some u4 minus v4. You make some restriction. If you don't allow it to go unrestricted, you make some restriction. So you just rewrite x4 as some introducing new variables, u4 minus v4, something minus the other. So you bring it into the fold. You bring it into a net. You bring it into a group. You make it to be restricted. Don't allow it to go unrestricted because it was given to be unrestricted when it was a minimization problem. Now that you are making it maximization, you have to make it restricted. That is something minus the other. You will get the value to be brought under control. You restrict it. So let us use some other variable, say u4 minus v4. That's all. So that what is the problem now becoming in terms of new variables and new ideas brought in as a maximization problem? Hence, the problem becomes maximize W is equal to minus 2x1. Straight away, don't bother about minus Z now. It is now W in terms of the decision variables. Minus 2x1, minus 2x2, minus 4x3, minus of, what is x4? u4 minus v4. Subject to the constraints, 3x1 plus 2x2 plus x3 plus 9x4. What is x4? u4 minus v4 within brackets less than or equal to 60. 7x1 plus 2x2 plus 4x3 plus x4, that is u4 minus v4 within brackets, less than or equal to 24. Now, just look at, we need to write there itself the decision variable, I mean, all those variables, basic and non-basic variables to be non-negative. What are they? In your original problem, you had x1, x2, x3, but no more x4 because x4 is u4 minus v4. So you write separately u4, comma v4. Now, where do you get S1, S2? Because you are going to make the constants to be equations. And here, as I mentioned in the previous example itself, that it is not necessary that you should add one slack variable. In another constant, you should subtract one surplus variable. It can be both the equations can have surplus, both the equations can have slack, something like that. Well, an equation, okay, it all depends on the inequality you have. It is not necessary that you should have one equation, one constraint to have less than or equal to, another constraint should have greater than or equal to. It's not necessary. It can be both of them can be greater than or equal to, both of them can be less than or equal to, one of them can be less than or equal to, other can be greater than or equal to. Okay, so here is an example where you have both the constraints have less than or equal to inequality. So what's happening then? Then definitely we are going to add, we are only going to add. So okay, you can write S1 comma S2, whether you are putting plus or minus, that depends on the inequalities that are available in your constraint, isn't it? Anyway, in this problem, both of them are less than or equal to, so you need to add the slack variables. So you can write maximize W equal to minus 2x1, minus 2x2, minus 4x3, minus u4. Now we can remove the bracket, plus v4, subject to the constraints 3x1 plus 2x2 plus x3 plus 9u4 minus 9v4 plus s1 equal to 16, because less than or equal to. So add next constraint 7x1 plus 2x2 plus 4x3 plus u4 minus v4 plus s2. Here also, the second one is also having less than or equal to infinity. I'm sorry, less than or equal to constraint inequality. Therefore, here also you need to add only s2. Okay. So don't be under the impression again, slack variable means s1, surplus variable means s2. Not like that. First variable 1, second variable 2, third variable 3, that's all. Plus or minus depending upon the addition and subtraction. Addition for less than or equal to, subtraction for greater than or equal to. Here both of them are having less than or equal to inequality, therefore plus s1 equal to 16, plus s2 equal to 24. Last one, x1, comma x2, comma x3, comma u4, comma v4, comma s1, comma s2 greater than or equal to 0. This example, I mean an exercise, you can try similarly, a similar problem. Yeah. Before we go to this particular simplex method, now let's just have a comparison as well as a distinction between graphical method and algebraic methods. In graphical method, graph all constraints as straight lines because they are linear. By plotting the points and joining them on the plane, the first quadrant, you get straight lines, including non-negativity restrictions. That means automatically x1 greater than or equal to 0, x2 greater than or equal to 0. So automatically it forms the positive side of your x1. Suppose you take x1 along the x-axis, x2 along the y-axis, then you have the positive, you have the plane first quadrant. So including non-negativity restrictions, graph all constraints. That is, we are drawing straight lines. Solution space consists of infinity of feasible points. Of course, we will not normally in practical problems that we are going to see. You plot about 3-4 points, automatically you will get a straight line. And of course, you can have good number, any number, for every value of x1, you will have corresponding value of x2 of your straight line equation. You can plot the straight line. That's the reason it's given infinity, but don't bother about it. Identify feasible corner points. So you have the common, that is the intersection of those two or three straight lines which are which are your constraints. You will find the common area, that is the feasible region or feasible solution space, from which you will take the corner points. Identify feasible corner points of the solution space. Candidates for the optimum solution are given by a finite number of corner. Candidates means the points again here. The points for the optimum solutions are given by a finite number of corner points. Naturally, you'll have only 3 or 4 or 5 corner points. Use the objective function to determine the optimum corner point from among all the candidates. Candidates means again points here. So from among the points, by finding the values, by substituting the values of x1 equal to x2 equal to the original or your objective function, the minimum value is the minimization, maximum value gives the maximization. That's all about your graphical method. So when it comes to algebraic method, that which we are going to do by simplex method or dual simplex method or two-phase method, big M method, all those methods are naturally formed, known as algebraic method because you are dealing with the equations and tables and then iterations you are doing. Okay, right. So what's the difference now? Represent the solution space by M equations in N variables and restrict all variables to non-negative values. The same idea. The system has infinite number of feasible solutions. Okay, same. Determine the feasible basic solution of the equation. So here you will be finding in your iterative, because in algebraic method, the main thing is that you are going to do iterations by in terms of tabular columns, where you will be finding basic solutions and feasible basic solutions. That is basic solutions that satisfy all the constraints. Candidates means again points for the optimum solution, or the unknowns or the variables for the optimum solution are given by a finite number of the basic feasible solutions. Their corner points here feasible solutions, BFS, basic feasible solutions. Use the objective function the same way as used in the graphical method to determine the optimum basic feasible solution from among all the candidates. Here, in fact, by doing iterative methods and in the tabular forms, you are going to exactly see, and the objective function maximum value or minimum value is directly in fact available in your tables. Okay, that is the way that it has a distinction in algebraic method over graphical method. Okay, so before we go to the simplex method that we will be taking it up later, I will come back to this graphical method and do some problems. So let us continue after 5 minutes break. A dealer sells two articles A and B. He earns rupees 2 and 3 when he sells one piece of A and B respectively. He earns. He buys these articles at the rate of rupees 1 and 2 respectively in the morning and sells them out in the evening. So buying price, selling price are given. He invests only rupees 100. Formulate the LPP to maximize the profit. So this itself is the formulation. When you are given in descriptive nature, how do you formulate it as an LPP, linear programming problem? That is, it should have the characteristics of maximize or minimize. The objective function is equal to involving decision variables and constants. That is z equal to c1 x1 plus c2 x2 plus etc plus cn xn depending upon the number of decision variables and subject to the constraints. Okay, that is what exactly we mean by formulation of LPP is done now here by an example. Let the dealer sells, so you should know number of pieces being sold out to get the profit, isn't it? X1 pieces of, because you have to bring in the variable of A and X2 pieces of B respectively. So now you need to go for profit. So maximize. Is it equal to, because he earns 2 rupees per piece. Number of pieces sold X1. So 2X1 plus number of pieces of B variety sold X2 and seller sold at 3 rupees per piece. So 2x1 plus 3x2 is your objective function, which is to be maximized. So objective function, maximization, subject to. What is the constraint? 1x1 plus 2x2. That is, he buys at the rate of 1 rupee per piece. So 1 into x1 for x1 pieces, buying price. And 2x2, buying price for x2 number of pieces for of B. So what is the total buying price? X1 plus 2x2. He invests only rupees 100. So less than or equal to 100. So don't put, when we say he invests only 100 means don't put equal to 100. It is less than or equal to 100. So that is the only constraint is given. So next you should always give about the non-negativity of the basic variables. That is decision variables. Decision variables. Okay. What are the decision variables here? X1 and X2. Number of pieces being sold of variety A and variety B. And the number of pieces sold cannot be negative. So it should be greater than or equal to 0. Okay, right. So this is yet another problem. And this is very famous problem named after Ready Mix company. So it is popularly known as Ready Mix company problem. Ready Mix produces both interior and exterior paints from two raw materials, M1 and M2. The following table provides the basic data of the problem. Tons of raw material per ton of exterior paint, interior paint. Raw material 1, using raw material 1 or from raw material M1, 6 exterior paint, 6 tons. And interior paint 4. Maximum daily availability 24 tons. Raw material 2, he manufactures or produces 1 ton of exterior paint, 2 tons of exterior paint. Maximum daily availability 6. Profit per ton $1,000 in dollars. So exterior paint profit $5,000 and interior paint $4,000. A market survey indicates that the daily demand for interior paint cannot exceed that for the exterior paint by more than 1 ton. So that is the difference between interior paint demand, daily demand, and that of the exterior paint by is 1. So this cannot exceed exterior paint by more than 1. So daily demand of for interior paint minus that of exterior paint cannot be more than 1. So less than or equal to 1. Also, the maximum daily demand for interior paint is 2 tons. Okay. So Ready Mix wants to determine the optimum, that is the best product mix of interior and exterior paints that maximizes the total daily profit. So this is to be formulated as an LPP. For the ready mix problem, we need to determine the daily amounts to be produced of exterior and interior paints. Thus the variables of the model are defined as, you have to have the number of the tons of exterior paint produced daily and interior paint. Exterior paint, let it be X1, number of tons produced. Of exterior paint, interior paint X1, X2. Exterior X1, interior X2. So to construct the objective function, see, we note that the company wants to maximize, that is increase the profit, isn't it, as much as possible. The total daily profit of both paints, that is important. So given that the profits per ton of exterior paint and interior paints are 5 and 4 given in the table in $1,000 respectively, it follows that total profit from exterior paint. Now what will happen? X1 is the number of tons produced. Profit selling price 5,000, isn't it? So total profit. So 5x1 $1,000. Total profit from interior paint 4x2 $1,000. Letting Z represent the total daily profit in thousands of dollars. What is the objective function? The objective of the company is to maximize the profit. So maximize Z equal to 5x1 plus 4x2. So in simple term, if you just want to make this phrase to be an LPP to start with an objective function, it is the maximization of the profit Z equal to 5x1 plus 4x2, where x1 is the number of tons of exterior paint produced daily, and X2 is the number of tons of interior paint produced daily, where the profit by selling exterior paint is $5,000. It is 5x1 per ton and $4,000 per ton of interior paints. So that now total profit is now 5x1 plus 4x2. That is your objective function, which is to be maximized. Okay. What else is given? They are the constraints, isn't it? Next, we construct the constraints that restrict raw material usage and product demand. There are two constraints. One is raw material usage, another is product demand. The raw material restrictions are expressed verbally as usage of a raw material by both paints is less than or equal to maximum raw material availability, isn't it? So you are using raw material by both paints should be less than or equal to maximum raw material availability. So daily usage of raw material M1 is 6 tons per ton of exterior paint and 4 tons per ton of interior paint. Thus, usage of raw material M1 by exterior paint is 6x1 tons per day. And usage of raw material M1 by interior paint is 4x2 tons per day. Hence, so what is the condition now? What is the total now? For 6x1 plus 4x2. So what is the condition now? It is less than or equal to maximum raw material availability. Usage is 6x1 plus 4x2. That is less than or equal to 24. Isn't it that we are going to write? In a similar manner, usage of raw material M2. This is usage of raw material M1 by both paints. So 6x1 plus 4x2 tons per day. Similarly, usage of raw material M2 by both paints is 1x1 plus 2x2 tons per day. So it is given in the table. 6x1 plus 4x2 is less than or equal to 24 raw material M1. x1 plus 2x2 less than or equal to 6 raw material M2. And there is one more thing is given. The first demand restriction stipulates that the excess of the daily production of interior over exterior point, that is x2 minus x1, should not exceed 1 ton, which means that x2 minus x1 should not be greater than 1, means less than or equal to 1. That is the market limit for the demand. Okay, that is the market limit. Next is demand limit. The second demand restriction stipulates that the maximum daily demand of interior paint is limited to 2 tons. So x2 is less than or equal to 2 demand limit. Okay, so you have now 4 constraints. So everything an implicit for understood to be restriction is that variables x1 and x2 cannot assume negative values. What is implicit? What is to be understood? They are being number of tons per day produced, exterior, interior paint, so they cannot be negative. So x1, x2 greater than or equal to 0 is non-negativity of the decision variables, and that is the end of it. That's the last line. So you have now 4 other constraints. What are they? 6x1 plus 4x2 less than or equal to 24. x1 plus 2x2 less than or equal to 6. Say, suppose you want to write in that order, minus x1 plus x2 less than or equal to 1 and x2 less than or equal to 2. x1, x2 greater than or equal to 0. Original objective function maximize z equal to 5x1 plus 4x2. So this is what exactly the formulation of ready mix problem. Okay. And here you may have one doubt. Sir, we have written minus x1 plus x2 less than or equal to 1. Can we have minus x1? No problem, because x1 decision variable is given as greater than or equal to 0. So don't bother about minus x1. Similarly, look at the right hand sides there. The constants are non-negative. Okay, right. A similar problem. Okay, exactly a similar problem. You can see for yourself. Everything is clearly given in the same fashion. So finally, the linear programming model for this example can be summarized as maximize is equal to 13x1 plus 11x2 subject to the constraints. See, sometimes the constraints may not be there, so don't bother about. So whether if the word constraints are not there, whether it is constraint or not, subject to means it is subject to the constraints. So the constraints can be explicitly given or may not be given. It is understood. Okay. 4x1 plus 5x2 less than or equal to 1500. 5x1 plus 3x2 less than or equal to 1575. x1 greater than or equal to 0. I mean, x1 plus 2x2 less than or equal to 420. x1 greater than or equal to 0. x2 greater than or equal to 0. Again, here you may have one doubt. Sir, it is given separately x1 greater than or equal to 0, x2 greater than or equal to 0. Normally, we write all those decision variables in one step only. x1, x2 greater than or equal to 0. That's enough to show that, to emphasize the non-negativity of the decision variables. Here again, just look at, as I already mentioned in the beginning itself, there need not be any correlation between the number of constraints and the number of decision variables are available, because here you just have only 2 decision variables, but there are 3 constraints. So there is no connection between these 2. Okay. This is what already we have talked about. The same thing was already mentioned. How do you go about doing the graphical solution methods? Okay, right. Let S be the convex region bounded by the lines of constraints. Then the objective function attains its extreme values at the vertices, that is corner of the region. What are the steps? Plot the line corresponding to each constraint. It may be you may have less than or equal to or greater than or equal to, but you take the equal sign, because for straight line, you know how to make a graph by plotting points, how to make a straight line. You need to have only equal to, isn't it? Okay. So when it is less than or equal to means it is those area falling below the line. Greater than or equal to area falling above the line. That's the meaning. That's all. Otherwise, you cannot draw. You have to have it as equal to. Determine the feasible region and indicate it by shading the common area. That is the feasible region. Determine the coordinates of each vertex of feasible region. So you have more corner points in your feasible region, and you have to take the appropriate one which gives the maximum for maximization, minimum. Find the value of Z at each vertex and get the maximum value or minimum value as the case may be. All these things I already explained. So this is this. So start from a corner point of FSS feasible solution space and identify the direction in which objective function gets optimized. This reduces the search of optimal solution from feasible space of infinite points to only finding the corner points, finding from corner points. The solution of ready mix problem by graphical method. So already we have formulated as an LPP the ready mix problem just few minutes back, and we are now ready with the LPP straight away. That the complete ready mix model is maximize z equal to 5x1 to 4x2, subject to the constraint x1 6x1 plus 4x2 less than or equal to 24, x1 plus 2x2 less than or equal to 6, minus x1 plus x2 less than or equal to 1, x2 less than or equal to 2, x1 comma x2 positive. So now we are going to solve this LPP by graphical method. This type of problem can also be expected from exam point of view, which is very simple. Just look at it. Draw on a sheet of paper. Now, no need to go to graph sheet. You can just plot the points, make axis. There are only two variables now. X1 axis horizontal, X2 axis vertical. So you just know the numbers are there. So accordingly you can write. See, on the x1 axis, you write 1, 2, 3, 4, 5, 6, 6, and here 1, 2, 3, 4, 5, 6, etc. So next, you have to take the first straight line. 6x1 plus 6x2 is equal to 24. You should only take the constraints and you take them as straight lines as equal to. Okay, so you now make the table. You know very well, isn't it? X1, X2, you give various values, only positive values. Then you will be able to plot a point that satisfies the equation. You take about some 3-4 points, because you know very well 2 points are enough to make a straight line. But if you just make only 2 points, you may not be able to sometimes get the intersection of the line with the other line, so that you will be perplexed. You will be wondering where is the feasible region. Therefore, you just can have about 3-4 points. For example, see 6x1 plus 4x2. Immediately what will happen? Put x1 equal to 4, x2 equal to 0. Isn't it? 24 plus 0, 24. So x1 is 6. What is x2? 0. So the point is 6, 0. Okay. Next, you can think of x2 equal to 6, x1 equal to 0. So 0, 6. So look at this point. It is 0, 6. Then you can have here 3 into 6, 18, plus 4 into, no. You can think of so many things like that, no? 6 into 2, 12. 4 into 3, 12. 12 plus 12, 24. So it is 2, 3. Where is it? This is 2 and this is 3. Isn't it? So like that, you will have, so at least you take one more point. So so that you will have an equation. Is it right? Again, suppose you have 4 here. Here it is 0. So you have 4, 0, 1 point. 2, 3 is another point. 0, 6. Enough. To draw the line. This is line 1. Why arrow mark is put down? Because 6x1 plus 4x2 less than or equal to 24. So it is this area bounded by this x2 axis, x1 axis, and the straight line 6x1 plus 4x2 equal to 24. So it is, so the less than or equal to 24 means if you just shade this rectangle triangle, that is less than or equal to, except the boundary. Isn't it? So the boundary is your straight line. You need boundary, isn't it? That's why you have to make it as equal to. So next you take equation 2. x1 plus 2x2 equal to 6. x1 6, x2 0. Okay, this is. Then x1 0, x2 3, 0, 3. See? Okay. Then any other point? This is and then 3, 3, so will it be 1.5, 1 by 2? 0.5, 3 plus 3 by 2. Yeah, this x2 is 3 by 2, x1 is 3. So 3 plus 3, 6. That is, this is 3 and this is your C is your 1.5, 3 by 2. You get the second equation. So look at 0, 3, 6, 0, 3, 1.5 is your point. Okay, it is a straight line 2. So you put an arrow mark down. Not necessarily you have to put an arrow mark. You just put the straight line, that's enough. Then minus x1 plus x2 equal to 1. That is, x2 is equal to, that is x1 minus x1 plus x2 equal to 1. That is, if you put x1 equal to third equation, you just put, you put 1, 0, comma 1. That is, this is 0, this is 1. You get 1. And then if you put 2, comma, if you put here, x2 is 3, x1 is 2. So 2, comma 3. 2, comma 3. So you get minus 2 plus 3, 1. So you get third equation. Okay, this equation. And fourth, x2 equal to 2. x2 equal to 2 is a straight line parallel to your x-axis, x1 axis, isn't it? At the distance of 2. This is your line x2 equal to. Thus, you have 4 straight lines. 1, 2, 3, 4. Okay, these two, the last 5 and 6 are nothing but decision variables are non-negative. Okay, now you can easily find out the points. Already we have easily found out, isn't it? See, you have a point here, 6. You have this is 6, comma 0, 4, comma 0, and this is 0, comma 3, this is 0, comma 6, isn't it? This is 2, comma 3, 3, comma 2, comma 3. This is 4, comma 0, comma 2. All these things are there. Now you just look out. Shade the region which is enclosed, that is common between all the straight lines, that is all the regions rather, all the constraints, means all the conditions, all the regions. So you just see that which is common, only this. Look at the shaded region. That is called a solution space or feasible solution space, or simply known as FSS. So they are just denoted by the points A 0, comma 0, B 4, comma 0, C 3, comma 1.5, D 2, comma 2. Yeah, 2, comma 2. Isn't it? Second equation. Then this point is no 0, comma 2. This is 0, comma 2. And then E is 1, comma 2. Isn't it? 1, comma 2, third equation. And then F 0, comma 1. So these are all the corner points A, B, C, D, E, F, which are forming the feasible region or feasible solution space. Now, at each of these points, find out the value of Z, the objective function. Okay, right. Look at the corner points are already I have mentioned now. I have also shown you how you got the point. F10, E12, D22, C3 1.5 and B40. The values of Z at these points are 5, 13, 18, 21 and 20 respectively. How do you get this? Just go to the function. What is the first point? We had 1, 0, then 1, 2, for example, isn't it? 1, 0. So you get x1 is 1, x2 is 0, 5. Then 1, 2, 5 plus 4 into 2, 8, 13. Then 2, 2, 10 plus 8, 18, like that, isn't it? So at every point you get. So value of Z at F, 5. Value of F Z at E, 13. Value of Z at D is 18. Value of F Z at C is 3, 1.5. That is 21. Then at B, 20. You can easily find out. Substitute for x1 and x2 respectively. So these are all values of Z at the corner points in the feasible solution space. So the question is maximize. That means find the maximum value of Z. What is the maximum of these values? 21. The maximum value of Z is 21 at the point C. Isn't it? Okay. So that's how will you write max instead of writing maximum, because maximize is a question. So you are finding maximum value of, which you can shortly write max is equal means maximum of the objective function is equal to 21 is an equation. Exercise, solve graphically. Another problem. A machine can produce two types of particles, A and B. The rate of production is 3 pieces of A and 4 pieces of B per hour. The owner of the machine earns rupees 2 and rupee 1 per piece of A and B respectively. He is required to supply minimum 10 and 15 pieces of A and B respectively. Formulate the problem if the machine works for 8 hours and can solve it by graphical method. So here you have to first formulate the problem as an LPP, then you solve it by graphical. See, well, we have formulated the problem. Well, you have to do it. That's another problem. That is exercise. This is another problem, minimization problem. The same way. Minimize means after finding all these things, you take the minimum value. Okay. See, I will show you this. You have the graph. You can draw the intersecting lines. You can draw the two lines, 2x1 plus 4x2 greater than or equal to 16 and 4x1 plus 3x2 greater than or equal to 24. So you can see the intersecting space, that is feasible region, and then get the corner points. This is the solution given straight away. Now I have explained here. You have to do all those things of solving those two equations are the points of those two straight lines automatically. They will form the corner points of the feasible region. A 0.8, B 4.8, 1.6, and C 80. You can do it by yourself. Easy. Then you find out values of Z at these corner points 24, 33.6, and 48 respectively. So what is the function? 6x1 plus 3x2. Okay. 6x1 plus 3x2, 3 into 8, 24. Then 6 into 4.8, 28.8. Then 3 into 1.6, 4.8. So you get 33.6. Then 6 into 8 plus 3 into 0, 48. So of the three values, which is the least, 24. Therefore, the minimum value of Z is 24 at the point A. See, A, B, C is after all the letters that you are giving. Anything can be A, anything can be A. Okay. Suppose the problem is the maximum, then maximum value is 48. So now, unboundedness. Now, is there any possibility that this is what exactly I touched in the beginning itself, that infeasibility? There can be a problem which has no solution. Yeah, we have seen, isn't it? If you again go back to the solving of linear algebraic equations, system of linear equations, and you have seen that by reducing the augmented matrix A comma B and finding the rank of the augmented matrix to be, if they are equal and number of unknowns, it is consistent, but it has a unique solution. Equal, consistent, but less than the number of unknowns, infinite number of solutions. The ranks are not equal, system is inconsistent, means there is no solution. That is what here we mean in terms of the word infeasibility. It's not possible. It is infeasible. Okay. So whenever you have, so as you know very well that a system can have solution, need not have any solution. If it has a solution, it can be unique or it can be finite number of solutions, isn't it? So there is a possibility of having no solution. The same thing here we are going to see by graphical method. It is a solution whose objective function is infinite. If the feasible region is unbounded, then one or more decision variables will increase indefinitely without violating feasibility, and the value of the objective function can be made arbitrarily large. That means it goes on up to infinity. Okay. Example. So here it says example. Now, suppose you take this problem take this problem. Solve graphically. Maximize z equal to 2x1 plus 3x2 subject to the constraints 2x1 plus x2 less than or equal to 2, 3x1 plus 4x2 greater than or equal to 12, x1 comma x2 greater than or equal to 0. So one is less than or equal to 2, another one is greater than or equal to 12. Okay, right. So let's see. Just look at this. The following graph gives the regions represented by the constraints. So this is the line x1 plus that is what is this condition? Let's go back. 2x1 plus x2 less than or equal to 2. Just look at the straight line which is shadowed with the horizontal and vertical lines. Okay, you have it is bounded by 1 0 on the x1 axis, 0 1 0 2 on the x2 axis. Is it right? 2x1 plus x2. So 2x1 plus x2. 2 into 1 plus 0. So equal to 2. If you take 0 comma 2 again, 2 into 0 plus 2 equal to 2. So you have that result, isn't it? Okay. So you have this region 2x1 plus x2 less than or equal to 2 in the top, in the bottom, isn't it? This is yours here. And this is your 3x1 plus 4x2 greater than or equal to 12. So you have 3x1 plus 4x2, that is 3 into 4 plus 4 into 0, isn't it? So 4 comma 0. If you take x2 equal to 3, x1 equal to 0, 0 comma 3. So you have 0 comma 3 on x2 axis, 4 comma 0 on x1 axis, and that it is greater than or equal to 12. So the region that is being shaded will be above the boundary line 3x1 plus 4x2 equal to 12. So all those points, the region will be shaded because it is greater than or equal to this line. Greater than or equal to. So this is above the line and this is below the line x1 plus 2x1 plus x2 equal to 2. So now that between these two regions, there is nothing common. There is nothing common, isn't it? So it has no solution. From the graph, we find that there is no common region between the two. That is to say that there is no point x1, x2 which satisfies both the constraints. Hence, there is no feasible solution. Thus, the given NPP has no solution. Okay. Alternate optimum. So this point also already we have seen. We had seen unique solution. We had seen example of no solution. Now we will see an example of multiple solutions. Okay. Any system of algebraic equations can have unique solution, can have multiple solutions, can have no solution. It's all possible. So we have seen examples of unique solution and no solution just now and multiple solution. Just read that. Alternative. Maximize z equal to x1 plus 2x2 subject to x1 less than or equal to 80, x2 less than or equal to 60, 5x1 plus x2 less than or equal to 600, and also one more constraint x1 plus 2x2 less than or equal to 160. Of course, decision variables x1, x2 greater than or equal to 0. Okay. Now, if you plot these four constraints, we have four straight lines. What are they? This straight line is your 5x1 plus 6x2 equal to 600. And this straight line is x1 plus 2x2 equal to 160. And this is the line x2 equal to 60. And this is the line at x1 equal to 80 parallel to your x2 axis. So now if you look at what is the region that is common to all these four lines, you have not this rectangle, because still there is a restriction constraint. Therefore, if you just look at the shaded region, shaded with some cross lines, you can look for the points on the boundary of this feasible solution space to be U, P, Q, R, T. These are the corner points. Okay. Now, what's happening? Let us find values of the objective function is set at these points. What's happening? Let us see. In the above figure, there is no unique outermost corner cut by the objective function line. All points from P to Q lying on line PQ represent optimal solutions, and all these will give the same optimal value, maximum profit of rupees 160. And what is the meaning? This is indicated by the fact that both the points P and Q with coordinates 40, 60, 60, 50 are on the line. Just look at what's the meaning? P. P is nothing but 40, 60. Okay. So where is it now? 40 plus 2 into 60. 40 plus 120, 160. It is on this line. So P lies on this line. Then Q. What is its coordinate? 60, 60, I think 50. So 60 plus 100, 160. So both the points 40, 60, 60, 50. 40, 60 and 60, 50 are on the line. X1 plus 2, X2 equal to 160. So what's happening then? All points from P to Q lying on line PQ represent optimal solutions, and all these will give the same optimal value of rupees 160. So you have more than one. It is P and Q and more points between P and Q. That means it is not the only solution P alone or Q alone. You have multiple number of solutions. Okay. Thus, every point on the line PQ maximizes the value of the objective function, and the problem therefore has multiple solutions. So this is what already I have discussed in detail. So practice problem. You can try your handset, solve graphically. Okay. Well, thank you.